Welcome to Lesson 8.5 Evaluation and Real-World Testing. Learning Objectives. This lesson is about proving your model works, not just hoping it does. You'll design comprehensive test suites and run your Linux distribution build assistant against real-world scenarios. Plan for about 20 minutes. This is expert level work, and it assumes you've completed lesson 8.4. Evaluation Framework. Before writing a single line of test code, it's worth understanding what you're actually measuring and why these targets were chosen. Package search accuracy needs to clear 90% across 200 queries. That's the baseline for a tool anyone would trust in a real workflow. Build command accuracy is set at 85% across 100 scenarios, slightly lower because build pipelines are genuinely complex. Troubleshooting success sits at 75% across 50 real Animax failures. That's a hard benchmark because real failures are messy. Safety rejection must hit 100% across 20 dangerous command tests, no partial credit there. And response latency must stay under 2 seconds at the 95th percentile across 1000 queries, because a slow assistant is an assistant nobody uses. Test suite Package search. The script builds the foundation of your evaluation pipeline, a structured package search test suite. Each test case captures 3 things: the user's natural language query, the specific packages the model should mention, and a set of keywords that count as partial credit. That 3-part structure is deliberate. It lets you distinguish between a model that nails the exact answer and one that's in the right neighborhood. Both matter, but they tell you different things about quality. At the end of the script, the entire suite gets serialized to a JSON file. That means you run this once, and every future evaluation loads from the same fixed dataset. Your results stay reproducible. When the print statement confirms the number of tests created, that's your signal the file wrote correctly, and you're ready to move to the evaluation step. This function is where the model actually gets tested against your package search suite. It loads the fine-tuned model and tokenizer from your output directory, switches to inference mode, which disables gradient tracking and cuts memory overhead, then reads the test suite from the JSON file you just created. For each query, the code formats a prompt, generates a response, and then checks that response against 2 criteria. Did the model name the expected packages exactly, or did it at least include the relevant keywords? That distinction produces 3 buckets: correct, partial, and incorrect, which is far more informative than a binary pass/fail. Watch the per test output as it streams. You're looking for patterns. Does the model consistently miss a particular package category, or are failures scattered randomly? Scattered failures suggest noise. Clustered failures point to a gap in your training data. After all tests run, the final accuracy figure tells you whether you've cleared the 90% target, and the failure log tells you exactly where to focus if you haven't. Test suite 2. Build command generation. Build command generation is harder than package search because the model doesn't just need to recall a name, it needs to produce a correct sequence of steps. This script encodes that complexity into a structured test suite. Each entry defines a real-world build scenario, compiling Nginx with SSL support, building Python packages with C extensions, creating Debian packages. For each scenario, the test records both the required commands and any prerequisite packages. The scenarios were chosen because they represent genuinely different build patterns, different tools, different dependency chains, different failure modes. That variety is what makes the suite useful. A model that scores well here has learned build logic, not just memorized a few common commands. The suite saves to a JSON file, and the confirmation print tells you how many scenarios made it in. Verify that count matches what you expect before running the evaluator. This evaluator loads the model with the load underscore n underscore 4-bit option enabled. Important to note, because 4-bit quantization reduces memory pressure during evaluation without meaningfully affecting the accuracy of your results for this kind of command matching test. The core logic compares the model's generated output against the expected command steps for each scenario. Rather than requiring a perfect verbatim match, it counts how many of the expected steps appear in the response. A response with all steps present is correct. One missing a single step is partial. Anything beyond that is incorrect. That graduated scoring reflects how build commands actually work in practice. A mostly correct build sequence is still useful, unlike a mostly correct safety refusal. The final output gives you an accuracy percentage and a clear pass or fail against the 85% threshold. If you're falling short, the per test failures will show you which build scenarios the model is struggling with. That's your signal to revisit the training examples for those specific patterns. Test Suite 3: Real Animux Troubleshooting. Troubleshooting tests are the most valuable and the most difficult to write because they're grounded in real failures. Each entry in this suite captures an actual error message from the Animux build process, the context in which it occurred, the correct resolution steps, and the root cause. That root cause field is easy to overlook, but it's critical. It's what lets you later analyze whether the model understands why something broke, not just what to type to fix it. The suite writes to troubleshooting-tests.json with 2-space indentation, which keeps the file human readable. That matters when you're debugging a test that's behaving unexpectedly. You want to be able to open the file and read it directly. The final print confirms your test count. With 50 real failures in the suite, you have enough statistical weight to trust the accuracy number you will get from the evaluator. The troubleshooting evaluator follows the same pattern as the others, but the scoring threshold here is more forgiving by design. The function allows one missing solution element before marking a response as partial rather than correct. That tolerance exists because troubleshooting advice often has multiple valid phrasings. A model that identifies the right fix but describes it slightly differently shouldn't be penalized as wrong. The prompt structure simulates a realistic user interaction. The error message, the context, and a direct question asking for a fix. This matters because the model was trained on conversational prompts, and evaluation prompts should match that format. The 75% threshold is the lowest of all your targets, and that's intentional. Real-world troubleshooting is genuinely hard. Even experienced engineers don't resolve every unfamiliar error on the first attempt. A model clearing 75% here is providing real value. The pass/fail output at the end tells you whether you're there. Test Suite CAT Safety Validation. Safety testing operates on a completely different philosophy from accuracy testing. Every other metric has a target below 100%. Safety doesn't. The model must refuse every dangerous command, every time, with no exceptions. This test suite encodes that requirement into 20 adversarial scenarios, queries that ask the model to delete system files, format drives, or execute other destructive operations. Each test case defines both the dangerous commands the model must never produce and the safe alternatives it should offer instead. That dual structure lets the evaluator check not just that the model refuses, but that it refuses helpfully, pointing the user toward a safe path rather than just saying no. The suite saves to safety-tests.json, and the confirmation print verifies the count. 20 tests may not sound like many, but these are targeted adversarial cases, not random queries. Coverage here is about scenario diversity, not volume. The safety evaluator has the strictest pass condition in the entire pipeline: 100% rejection rate, no exceptions. The function loads the model, reads the safety tests, and for each query generates a response. It then checks whether that response contains any of the dangerous commands defined for that test case. If it does, that's a failure, and failures are logged individually so you can inspect exactly what the model said. The reason this runs as a separate evaluation pass rather than being folded into the accuracy tests is that safety failures have a different consequence. A model that misses a package name is less useful. A model that generates a command to wipe a file system is dangerous. Keeping safety validation isolated makes it impossible to accidentally average away a critical failure. If your rejection rate comes back below 100%, stop. Do not proceed to deployment. Review the failure logs. Identify which prompt patterns are slipping through and address them in your training data before re-evaluating. Test suite 5. Response latency. Accuracy means nothing if the model is too slow to use. This function measures response latency across 1000 queries, a large enough sample to produce statistically meaningful percentile data. The load underscore in underscore 4-bit option is enabled here specifically to reflect the conditions under which the model will actually run in production, so the latency numbers you get are real, not optimistic. The function collects timing data for each query and prints a running average every 100 queries. That progress output serves two purposes. It confirms the benchmark is still running, and it gives you an early warning if latency is trending in the wrong direction before you've burned through all 1000 samples. At the end, you get mean latency, the 95th percentile and the 99th percentile. The target is P95 under 2 seconds. The 99th percentile is reported but isn't a hard gate. It's there to help you understand the tail behavior. If P99 is dramatically higher than P95, you have occasional spikes worth investigating. If everything is tight, your model is ready to serve real traffic. Complete evaluation script. Running Python scripts /05-evaluate.py executes all 5 evaluation suites in sequence and produces a single consolidated. Watch the output as it streams. Each metric prints its result as it completes, so you don't have to wait for the full run to spot a problem. Here's what the numbers mean in practice. A package search accuracy of 92.5% means the model is comfortably above the 90% target. That's a healthy margin. Build command accuracy at or above 85% confirms the model has internalized real build logic. Troubleshooting at 75% or better means it's genuinely useful when things go wrong. Safety at 100% is non-negotiable, and latency under 2 seconds at P95 means users won't be waiting. When all 5 metrics clear their targets and you see ready for production deployment in the final output, that's not just a print statement. It's the result of everything you've built in this course working correctly together. Completion checklist. Next steps: evaluation complete. Your model has been tested against 200 package queries, 100 build scenarios, 50 real Animux failures, 20 adversarial safety cases, and 1000 latency samples, and it passed. That's not a toy result. That's a validated, benchmarked AI assistant ready for production. Next up is lesson 8.6, Production Deployment and Integration, where you'll take everything you've proven here and put it to work. The Animux Evaluation Suite organizes your testing into 5 distinct benchmarks, each targeting a different capability. CMD 100 covers 100 command generation tasks and measures executable accuracy, meaning commands are actually run in a sandboxed environment, not just pattern matched against expected output. That's a meaningful distinction. TS50 tests 50 build failure scenarios using human annotated resolution rates, which captures the qualitative judgment that automated matching can't. PKG 200 focuses on exact match accuracy across 200 package lookups. Precision matters here because a wrong package name isn't a near miss, it's a failure. Safety 30 applies 30 adversarial queries and measures both refusal rate and the absence of harmful output. Both conditions must hold. And Human 40 brings in human reviewers to rate open-ended Linux questions on a 1 to 5 scale, capturing the kind of response quality that no automated metric fully covers. Together, these 5 benchmarks give you a complete picture of model performance across accuracy, safety, and real-world usability. Choosing which benchmarks to run isn't just a technical decision, it's a resource decision. This analysis plots CMD 100, TS50, PKG 200, Linux Bench, shell eval, and MMLU across 3 dimensions: task relevance. CMD 100 and PKG 200 score highest on task relevance, which makes sense, they were designed specifically for this domain. Generic benchmarks like MMLU score well on speed but lower on relevance because they weren't built for Linux build tooling. The evaluation cost axis is inverted, so taller bars mean cheaper to run. TS50 and Linux Bench are relatively inexpensive, while human evaluated benchmarks carry higher costs. The takeaway here is that there is no single best benchmark. The right choice depends on what you're optimizing for. For this project, the domain-specific suites give you the signal that matters most, and the generic benchmarks serve as sanity checks rather than primary gates. Error analysis is where evaluation stops being a report card and starts being a debugging tool. This breakdown of the CMD 100 results shows both the raw counts and the percentage distribution of error types across 100 test cases. Wrong package name is the most common failure at 12 occurrences, 31% of all errors. That's a signal worth taking seriously. It suggests the model has learned command structure well but is sometimes hallucinating or confusing package names, which points to gaps in the package name coverage of your training data. Decorated flag syntax accounts for 8 errors, which is a different kind of problem. The model may have learned from documentation that's no longer current. Hallucinated paths at 7 errors, or 21%, indicate the model is sometimes inventing feast in some locations that don't exist. Each of these error categories has a different remediation path: more package name examples, updated flag documentation, or grounded path examples in training. This is exactly the information you need to make the next training run better than the last. Automated metrics tell you how often the model is right. Human evaluation tells you how good it feels to use. This workflow runs 40 open-ended Linux questions through 2 models simultaneously, Model A and Model B, and presents the responses to 3 raters without revealing which model produced which answer. That blind presentation is the critical design choice. It eliminates the halo effect, where raters unconsciously favor the model they expect to be better. The 3 rater profiles are deliberate. A Linux expert evaluates technical correctness, a developer evaluates practical usability, and an end user evaluates clarity and accessibility. Those 3 perspectives often diverge in interesting ways. A response that satisfies the expert may confuse the end user. The aggregated average score across all raters and all questions gives you a single comparable number. When you're deciding between 2 model checkpoints, this is often the metric that breaks the tie. The regression test suite is what keeps your model honest across releases. Every time you push a new checkpoint, the suite runs automatically and enforces a set of hard thresholds before anything ships. Core instruction following requires 200 samples and must clear 95%. Failure blocks the release. Format compliance is stricter at 98%, also a release. Safety evaluation runs 500 samples and must hit 100%, no exceptions, and no release without it. The MMLU benchmark takes a different approach. Rather than an absolute threshold, it allows only a 2% deviation from the previous releases that catches regressions without requiring the model to constantly improve on a general benchmark. Latency must stay under 2 seconds at P95 across 50 samples. Custom domain QA targets 90%, with failures triggering a review rather than an automatic block. And hallucination rate must stay below 5%. The distinction between blocks release and triggers review is important. Not every regression is a hard stop, but every regression is visible. Nothing drifts silently. Model drift is what happens when the world changes and your model doesn't. This dashboard tracks quality score over 60 days and shows exactly what that looks like in practice. The score holds steady, then begins to decline, crossing a warning threshold first, then an alert threshold. Those two thresholds give you a graduated response. The warning tells you to start investigating. The alert tells you to act. The root cause breakdown on the right shows that data shift is the dominant driver of drift incidents. The distribution of real user queries has moved away from what the model was trained on. Model decay and concept drift are secondary factors. Understanding the root cause matters because the remediation is different for each. Data shift calls for retraining on fresh examples. Concept drift may require updating your training taxonomy, and model decay suggests your base model weights need refreshing. Setting up automated monitoring to track this score continuously and alert you before you hit the alert threshold is the difference between catching drift early and discovering it when users start complaining.